Hello everybody. In this video we're going to talk about one new topic in Aspen Plus, which is the solid handling. And solid handling is kind of different in many aspects in Aspen Plus, and that's why I'm making this video as an introduction. And for me, I believe that this is a very important introduction to anybody who is interested in working with solids in Aspen Plus, because there are some things here that I'm gonna mention in this video that took me personally some time to understand and grasp and uh, like understand how things are going in Aspen Plus, how the software understands the inputs, and how I can tell the software what I want to tell it. So before we start, I want just to draw your attention to some things that we passed by many times before, but we we didn't go into their details before. So this, for instance, is a screenshot of stream definition window. And as we all know, and we did this many times before, we define the stream by defining either temperature, pressure, or vapor pressure, or I mean vapor fraction, and then we define the temperature and pressure, for instance, the flow rate and the compositions, and this all what we use to define the stream. However, we never ever visited these two tabs, and as you see, they are always not active for all the cases that, and you can check that by yourself. These two tabs were never active before, and it seems that they have something to do with the solids, because this is called CI solids and this is NC solids. So it seems that they have something to do with solids. So we will understand what the CI and NC mean, and we will understand why these two tabs were always inactive, because this is a very important point. The second thing that we visited many times before is when we do the design specs, in the define tab, where we define the parameters that we want to adjust. For instance, if we want to adjust the stream variable, we choose the stream variable, then the stream name, and then this substream option is something that we used to see. And for almost all the cases that we, or always in all the cases that we visited, that this has only one option, which is mixed. So without going into the details of this substream or understanding what it means, we have no other option other than choosing mixed. So we choose mixed, and then we go forward. And this is something that we will understand today as well. What is the substream and what does it mean? So let's do the, or go for the first things first, which is the main things that we need to keep in mind while working with solids in Aspen Plus. And I tried my best to group all the concepts that I want to discuss in these four questions, which is why is dealing with solids in Aspen Plus different from dealing with liquids and gases. There are many things that we're going to talk about in case of dealing with solids that we never thought of or talked about when we were talking about the liquids and gases. And how the second question is how Aspen Plus classifies the solids, which is the CI and NC solids that we mentioned before. What do they mean? And then we will see what is, or understand what is the stream class and what is the substream that we just mentioned in the previous slide. And finally, what is the extra information, or if there are extra information that I need to define, so that I can define the solid fully in Aspen Plus. So let's go for the first question, which is why is dealing with solids different? Um, if we think about solids or liquids and gases, they are homogeneous phases. For a liquid phase, it's a homogeneous phase. The molecular structure of a gas or a liquid is always the same. If you take small amount of the liquid, you can predict the properties of the whole liquid if you know the properties of a small amount. But this is not the case for the solids, because there is one other, or some other properties that are different from a solid to another for the same type of solid. For instance, if I have like calcium carbonate, which is like some solid particles, you'll find that the particles will have different particle sizes, and this difference in particle size will change or affect the porosity between the particles, and consequently will affect the density. And that's why for those of you who studied unit operations, mechanical unit operations, I mean, they will remember that we mentioned something which is called the bulk density. The bulk density and the particle density. There are two densities for the solids, which is like a result of having some pores inside the solids, and the pores depend on the particle size. So this is something that you have to keep in mind. There is the moisture content. Some solids can keep some moisture, which is not the case for other solids, or some parts or particles will do this more than others. The particle size distribution, the particles are not all having the same size. They have different particle sizes, and that's why this is something that makes the solids different from liquids and gases. So from this, we cannot predict the bulk properties of a solid from the microscopic properties. I cannot get a small particle of the solid and say that I know the properties of this small particle of solid, so I can predict the properties of the whole like bulk of the solid. This is not possible. You have to define some more information. The third point, which is a pretty important point actually, which is the thermodynamic packages or models that we use in case of gases and liquids, is just one model. You can use a model for that can deal with liquid systems, the gas liquid systems, and we saw that many times before. We did some problems with liquid extraction, with distillation, absorption, with decanting, with many things that included many phases, either gas or liquid, or two liquid phases. And the software was working fine. I had no problem with dealing with the two liquids, because the thermodynamic model can deal with gas liquid equilibrium with the same equation, which is not the case for the solids. So this is why dealing with solids is tricky, and it's not the same thing that we used to do before for liquids and gases. Now let's go to the second question, which is the classification of solids in Aspen Plus. What is the CI solids and NC solids that we saw before? There are two types of solids that we can define in Aspen Plus, which is the conventional inert solids. The conventional is the same as conventional that we used to define the components before, which is the material that has a homogeneous molecular structure, such as the calcium carbonate, urea, whatever the solid that you have. You know the molecular structure well, so it's okay for you to deal with it as by just defining its molecular structure, the same way we defined the other things before. There are going to be some differences, but we will go through these differences when we visit the software. But for now, this is what we need to do. We need to know that this is just a material that can be defined by the molecular structure, and the software has all the information in the data bank, so there's nothing that you need to worry about after defining the components. I mean, there are the non-conventional solids, which are the solids that do not have homogeneous molecular structure. It's a blend or a mixture of different components, such as coal, such as pulp, and these things. So in this case, I cannot define them using the molecular structure as I did here, so I have to do some more work to define these components. So these are the non-conventional solids. So it's important to keep in mind that this is CI and NC are the components that I have. Now let's talk about what is called the substream. This is something in Aspen Plus that we need to understand well, because this is gonna let us understand some things that we didn't understand before, or we didn't visit before. So let's say I have a stream that contains conventional solids, non-conventional solids, and mixed phase, which is the gas and liquid phase. So something like this. So in real life, they're all mixed together and they're all flowing. Think of it like like a gas stream that has some solids suspended in it, or liquid that has some suspended solids, whatever the type of things that you have, but they are all flowing together. and this is what happens in real life. But in Aspen Plus cannot deal with them like this way, so you have to define each one of them separately. And to be able to define each one of them separately, Aspen Plus creates what's called a substream. So it breaks the stream into different substreams, which is a section of this stream. In this section, you can define the properties of each one of these streams separately. So I can define the liquid and vapor phase in the mixed part, and in the conventional inner solid, you can define the conventional solids if you have any, but in here you can define the non-conventional solids. And that's why in this tab or in this window we had a tab for mixed phase, which is for the liquids and phase and gases, and we have here the conventional inner solid, and here for defining the non-conventional solids. So this is the point that of having the substreams. So each tab of them represents one different substream. This is the point of this. So it's important for the user to understand what the substream means, and this is it's like taking place in the definition of the streams and in the results as well. So in the results you'd see, and this is something that we'll see in the future, that the results will be separated into different substreams. Each substream contains the temperature, the pressure, and all the information of this substream as if it's a separate stream, but they're all gathered together in one stream. So here will come one question, which is a very, very important question as well. So now we understand that there are substreams, and each one of these tabs is responsible for defining this substream. Why these two tabs were always inactive? I have no choice to put any information here. They are not active. It's the software is not letting me do anything here, and this is why we have the stream classes. So the stream class is something that we do in the very, very beginning, when we start working in the or with the Aspen Plus file, in the beginning of working in the simulation environment. And by choosing the stream class, we never chose the stream class because we didn't have to, but this is something that we will have to visit in the next videos. It dictates what, but I can choose any stream class, and we will see the stream classes in the next two slides. And in the stream classes, you can choose a class which tells, or you can tell the software that this stream class opens what type of substreams. So for the default, it's conventional stream class, so it lets the user only define the conventional or the mixed phase, which is the liquid and vapor phases. So there is no option for you to go for the conventional inert or non-conventional solids, because the stream class that you chose does not let you do anything other than defining the streams or the substream of the mixed phase. So I can choose another stream class that can open these for me, and this is the point of having stream class. So the user can set the stream class in the beginning of the simulation environment, and it dictates the types of phases you can, or substreams, this is the better word, which is the substream you can define in different streams. And it can let the user integrate the solids and fluids in one simulation. So before we see what stream classes that we have and why we have these different stream classes and the differences between them, there is one important point that we need to revise quickly, which is the particle size distribution or screen analysis. So we mentioned before that the solid will have different particles with different sizes or different diameters, and this is something that we need to know for some cases, like for screening, for crushing, for grinding, for all these things. You have to have a good idea about the particle size distribution. To do the particle size distribution, we do what's called screen analysis, and the screen analysis is having different screens with different opening size. The largest opening is in the top screen, and then it gets smaller till you get to the smallest opening in the very bottom. And by shaking them, the larger particles are kept here, and then smaller, and then here you will have the smallest particles. For each screen, it has a number that defines it, which is called the mesh number, And the mesh is simply the number of openings per linear inch. So you have here, let's say 20 openings, then this is mesh 20. If you have like 100 openings, then it's going to be mesh 100. So it means that 100 openings per inch, which means that it's smaller than the 20, the mesh 20. So the larger mesh is smaller opening size, and that's why this has the smallest mesh and this has the largest mesh number. So when you do this, you can measure the weight of the solids that has been or sitting here and here and here on each one of these screens, and we can end up with a table like this. It says that the opening diameter of the screen in millimeter, micron, whatever the size that you're using, and then the mass of solid that has been kept here, and the let's talk about this later. So let's see first these. So this says that there is 0 grams in the 130 millimeter diameter, so it means that all the particles are smaller than 130. Then 15 grams are sitting on the 120, so they couldn't pass from the 120, so they are smaller than 130 but larger than 120. And then 29 grams between 110 and 120, 55 between 100 and 110, and so on. Sometimes we like to calculate the cumulative mass of solids. So this tells us what is the mass of particles larger than specific diameter. So here this is 13 grams, which is larger than 10. Then 44, which is larger than 20, so it's just the addition of these two, and then the addition of this and this gives us this and this gives us 109, which is larger than 40, and so on. And we can plot them to get the famous particle size distribution graph, which is showing us how the particles are distributed for the particle diameter against the mass of solids, and this is the cumulative mass of solid. We can plot it as mass fraction, so that the values are linearized, so they're easier for the user to track them. Anyway, so this is very important information that we need to keep in mind. So this particle size distribution is abbreviated as PSD. So it's important to know that this PSD, what does it mean? So now let's go back to the stream classes. So we have 7 stream classes in Aspen Plus. And each stream class depends on the type of information or the type of streams or components that we have. So in case we have no solids, then there is no particle size distribution, of course. So we go for the conventional stream class, and this is the default, by the way. That's why in the conventional we don't have any option to define any conventional inert or non-conventional components. If we have conventional inert components with a particle size distribution, then we will go for mix CI PSD. CI goes or stands for the conventional inert, mix for the mixed phase, and the PSD. If not, we don't have particle size distribution, it's gonna be solid instead of PSD. The same for NC, it's mix NC PSD. If we don't have particle size distribution, it's mix NC. Then if we have both conventional and non-conventional solids, then we will have mix MCI NC PSD. If you don't have particle size distribution, it's gonna be mix CI NC. So if we choose any one of these, then we will have the tabs active depending on which stream classes we chose. This is where we do the choice. We go for setup, and here you go for stream class. You can pick which one that you are interested in, and here you can find more information. This is something that we will visit in the next video, inshallah. And here for the PSD defines the particle size distribution, and this is going to be another video that we are gonna go for. So I'll stop now for to this point. It's important for me to again visit the points that I wanted to make from the video. The first is why dealing with solids is different, and how solids are classified. It's important to know the different, or the what stream class mean and what substreams mean, and the particle size distribution as an extra information that we need to define so that the solid phase is properly defined in Aspen Plus. So this is all for today, and I'll see you in the next video, inshallah. Goodbye.